Assalamu alaikum. I am Dr. Muhammad Yasin from Department of Physics, University of Agriculture, Faisalabad, Pakistan. Today I am going to present some results of our research on production and testing of lanthanum zinc oxide carbon nanotube photocatalyst for the production of hydrogen as a green fuel. First of all, I would like to thank the organizer for providing me the opportunity to present our work in this prestigious event. Since I am from Faisalabad, which is facing the serious environmental pollution issue due to the fast industrialization and the population growth, the fast rising environmental pollution index of Asian countries is putting the human health on serious risk. And with the rapid evolution of industries, a substantial number of pollutants such as organic solvents, oil, and dyes are produced and discharged into the water resources, posing a serious problem of water pollution to the human health. The release of these contaminants into the water resources results in a deficiency of clean water, which is essential for the survival of human beings. These are the images of the environmental pollution taken from the internet sources for the different parts of the Faisalabad, especially the industrial areas of the Faisalabad, showing that how the environmental pollution is impacting the water and other resources which are directly related to the human health. The massive consumption of energy has raised the universal threat of rapid depletion of non-renewable fossil fuels due to the tremendous demand of energy to sustain the economy and ever increasing population of the world. Some recent reports suggest that about 85% of the world's total energy consumption comes from the burning of non-renewable fossil fuels, and the global warming and the other pollution in indices are witnessing continuous rise due to excessive burning of conventional fuels, which are being used to meet the energy demand of the world. So, for instance, many efforts are underway to find out eco-friendly approaches to deal with the energy and environmental challenges. Particularly, the photocatalysis is one of the most promising approaches which are being practiced for the remediation of environmental pollution. So photocatalysis is a kind of advanced oxidation process which has earned immense attention of the researchers to produce environmental friendly and inexpensive hydrogen energy to substitute the fossil fuels. Hydrogen is a high energy density green fuel which does not contribute any pollution to the environment. Therefore, the focus of this study is on the production of a hydrogen fuel through the photocatalysis by using the water and methanol as a source for the hydrogen. So here are different kinds of photocatalysts which are being used by the researchers to propose the efficient photocatalysis processes for the production of the green energy. Among them, zinc oxide is a semiconductor photocatalyst with a high oxidative potential, excellent photosensitivity, moderate stability, and variable band structure, which has sparked widespread interest in photocatalytic fuel production and environmental remediation. The zinc oxide has the band gap energy of 2.29 electron volt. When a sunlight interacts with the zinc oxide, it excites the electron from valence band to the conduction band, and these electron hole pairs drive the photocatalytic activity of the zinc oxide. However, this band gap suggests that this photocatalyst is only can work well under the UV region of the sunlight, but the UV part of the sunlight is only constitute 15%, sorry, 5%, and 40 to 45% of the sunlight falls in the visible region. So this photocatalyst does not work well under the visible region of the sunlight. It means a large portion of the sun spectrum is not usable if we consider this photocatalyst for photocatalytic activity. So it is necessary to modify this photocatalyst with some suitable dopants to reduce its band gap energy and to enhance its photocatalytic activity. However, there is another issue associated with pristine zinc oxide is that it does not respond well to the visible part of the light spectrum when used as a photocatalyst. The photocatalytic activity of the pristine ZnO is also hampered by the rapid recombination of electron-hole pairs and other factor which reduces photocatalytic activity is the photocollision. So these issues can be addressed by incorporating some suitable dopants, especially the rare earth oxides and lanthanum in particular, and by adding some carbonaceous products, for example, the carbon nanotubes. Rare earth metals are recognized for their large surface area and high charge carrier trapping ability, which can greatly reduce the recombination of oxidants. The greater ionic radius of rare earth ions compared to ZnO ions is expected to cause the lattice distributions in ZnO and some distortions in the structure, which can increase the lattice constant and hence reduce the zinc oxide band gap energy, making it suitable for the visible part of light spectrum. The uh, uh, another material which can effectively promote its photocatalytic activity is the carbon nanotubes. The carbon nanotubes can be employed as a support material for the production of efficient photocatalysts for the photocatalytic evolution of hydrogen and the treatment of the environment. Carbon nanotubes, as explained in this mechanism, works as a photosensitizer in a photocatalyst designed to generate large number of electrons during photocatalytic reactions. These electrons jump from the valence band to the conduction band of the photocatalyst and expedite the reaction rate by reducing the energy band gap of the photocatalyst. At the same time, carbon nanotubes acts as an electron sink, means the electron get trapped in carbon nanotube structure and therefore did not spontaneously return to the valence band without uh, uh, participating in the photocatalytic activities. These trapped electrons effectively contribute to the photocatalytic activity of the zinc oxide. So here is the procedure adopted to complete this research. First, we prepare the carbon nanotubes in the laboratory rather than buying the commercial one because they have different parameters and structural properties. We prepare the carbon nanotubes by ourselves with the desired structures. We use a substrate for the growth of carbon nanotube forest. We use the P-type silicon substrate covered with a SiO2 layer of 5 nanometer and then aluminum oxide layer of 15 nanometer, and these layers were deposited on the silicon using electron beam evaporation method. Then we use this substrate in a horizontal chemical vapor deposition reactor to produce the carbon nanotubes by using ethylene as a precursor gas and ferrocene as a catalyst for cracking the ethylene into carbon and hydrogen. The catalyst was placed in the high temperature zone of the reactor and the substrate was placed in the low temperature zone of the reactor when the ethylene carried by argon and hydrogen as a carrier and the and the poisoning prevention gases reach the catalyst. It cracks over the catalyst into the carbon and hydrogen. The carbon enters into the low temperature zone where it grows on the substrate in the form of the forest. And then these carbon nanotubes, along with the lanthanum, was used in a soil gel method to prepare a composite photocatalyst of lanthanum ZnO CNT. And then this photocatalyst, along with the pristine ZnO, was used for the production of hydrogen from the water methanol mix solution under the visible light from the sun. Here are the results of the research. First, we presented the same images of the carbon nanotubes produced using horizontal CVD method. The left top image shows that the forest type growth of carbon nanotubes, and the right top corner image shows a magnified same image of the same CNT forest. It shows a fine structures with uniform uh, diameter distribution of the carbon nanotubes. And these uniform distribution of the structures represents that there is a controlled growth of the carbon nanotubes. The bottom left image shows the same image of lanthanum ZnO carbon nanotube photocatalyst, and the right bottom image shows a magnified image of the left one. It clearly shows that there is a deposition of the zinc oxide and lanthanum on the surface of the carbon nanotubes by confirming the formation of the composite photocatalyst. These are the transmission electron microscopy images of the pure carbon nanotubes on the left hand side, showing some structural defects in the wall which are supportive for the reactivity with the zinc oxide and lanthanum. Right hand side show the tab image of the composite photocatalyst, which show the deposition of of the lanthanum and zinc oxide on the carbon nanotube structures. Then we conducted the XRD analysis to confirm the plane surfaces of the constituent materials in the photocatalyst. The XRD results clearly showed the presence of the planes of the carbon nanotubes, zinc oxide, and lanthanum. And then we try to check the composition of the constituents using the EDX analysis, and these analyses confirm that the carbon, oxygen, zinc, and lanthanum are present in the composite photocatalyst. Then we conducted the thermogrammatic analysis to check the stability of the structure and the residue present in the sample. We see that the pristine carbon nanotubes show low residue as compared to the composite photocatalyst. Since the composite photocatalyst consists of the different materials which have different temperatures of degradation, therefore the residue was much higher as compared to the pristine carbon nanotubes. So then we conducted the PL analysis, which are important to find out the the wavelength of the material where it is active, and this decides its the band gap energy. So the PL spectra of the as prepared photocatalyst is measured at excitation wavelength of 320 nanometers. These PL spectra confirm the typical ZnO emission band in the UV region due to electron hole recombination. It is also observed that the PL emission spectra of lanthanum ZnO composite and the lanthanum ZnO CNT composite shows a shift towards the longer wavelength as compared to pure ZnO, which identifies a decrease in optical band gap and it is supportive to the photocatalytic activity of the catalyst under visible region of the light spectrum. The UV band decreased in the order of ZnO, followed by lanthanum ZnO, and lanthanum ZnO CNT shows the lowest UV band as compared to the other samples. It is obvious that the combined effect of lanthanum and carbon nanotubes effectively reduce the recombination of charge carriers, which can be fruitful for the photocatalytic hydrogen evolution activity of the proposed photocatalyst. So then we perform the photocatalytic activity of the pure zinc oxide and composite zinc oxide for the hydrogen evolution activity. And these experiments were performed for consecutive 5 hours under the visible light. And the water ethanol mixture was split into the hydrogen and oxygen, and this hydrogen activity was noted after 5 hours. And it can clearly seen by the blue bar that the lanthanum ZnO carbon nanotube mixed photocatalyst produce highest hydrogen evolution rate as compared to the lanthanum ZnO and the pure ZnO photocatalyst. And the table at the bottom shows a comparison of the current study with the previously reported work. It is clear that in our study, zinc oxide in pure form produced 10.2 millimole of hydrogen in an hour, and lanthanum ZnO produced 145.9 millimole of hydrogen in an hour, and lanthanum ZnO carbon nanotube photocatalyst produce 184.8 millimole of hydrogen in an hour. These figures are much higher as compared to the previously reported results, which shows that the combination of the rare earth metals with the ZnO in the presence of carbon nanotube sport can effectively be used as a photocatalyst for the production of hydrogen and the degradation of the other organic pollutants. So another factor which is important in using a photocatalyst for hydrogen evolution or environmental treatment is its recyclability or stability, because these two factors adds to the economic value of the photocatalyst. So we repeated the 5 cycles with the same photocatalyst to check its stability over multiple cycles and its hydrogen evolution activity. If we see on the right side that there is no reduction in the photocatalytic activity of the composite photocatalyst over repeated 4 cycles of the photocatalytic activity. In each cycle, it produces almost similar hydrogen evolution rate, which show its high stability and recyclability under the similar conditions. So, conclusively, a forest-like growth of carbon nanotubes was conducted over SiSiO2Al2O3 sport by using a conventional horizontal CVD method, where the ferrocene was used as a catalyst and ethylene was used as a precursor gas. A set of pristine ZnO, lanthanum ZnO, and lanthanum ZnO carbon nanotube photocatalyst was produced using sol gel route and evaluated for photocatalytic activity under visible light illumination. And peer results shows that the composite photocatalyst in the presence of carbon nanotube spore show reduced recombination and increased transportation of charge carriers due to combined effect of lanthanum and carbon nanotube. The composite photocatalyst exhibited the highest hydrogen evolution rate of 184.8 millimole per hour under visible light illumination, as compared to 10.2 millimole per hour by the pure ZnO. The recyclability and stability of the composite photocatalyst revealed that hydrogen evolution rate did not decline during multiple cycling process. These findings suggest high stability and low process cost of the tested for composite photocatalyst. This study can promote the photocatalytic interest to design novel photocatalysts using the ZnO and